planet Earth, hundreds of millions of years in the future. Intergalactic explorers return to their home planet in search of signs of ancient civilizations. They find a planet that has changed beyond recognition. Gone are the familiar continents that we know today. Instead, they find a giant landmass with huge mountain ranges, massive frozen snowfields, and glaciers. The once thriving metropolis they seek has disappeared. A few broken remnants are all that remain, crushed and buried beneath tons of rock. Could this be a future vision of Earth? Naked Science asks, what forces could create such a bleak and barren world? And investigates how the awesome power of colliding continents shapes and reshapes our planet in an endless cycle of construction and destruction. Our world, the Earth. From space, it's easy to see the distinctive pattern of land that makes up the continents: North America, South America, Africa, Antarctica, Europe, Asia, and Australia. Giant landmasses separated by oceans that stabilize the environment with hospitable weather patterns, suitable for civilization and cities to evolve and prosper. Now imagine our planet ravaged by storm force winds, subjected to extremes of temperature, giant freezes, heat waves, and droughts. A world where cities are crushed and destroyed, where Africa tramples New York underfoot, and London freezes at the North Pole.
The geological future of New York is going to be rather traumatic. North America and Europe are going to collide with one another.
The world as we know it will be unrecognizable. This is not a portrait of the Earth after a devastating global disaster. This is how nature will shape our planet many millions of years in the future. This incredible remodeling is just part of a natural cycle that has shaped the Earth for the last 4 billion years, and will continue to do so until the sun finally destroys its surface once and for all. Today, our continents may seem solid, safe, and forever fixed in place, but they are none of those things. These great landmasses are constantly on the move. Speed up the last few billion years, and one can see the continents sailing across the globe. Powerful forces deep within the planet rip the continents apart and then smash them together in an ever-changing cycle of death and rebirth. Oceans disappear, mountains crumble, and rise again. Landmasses form and reform. Colliding continents are the mightiest force on Earth.
When we look at the history of planet Earth, we see that it is full of change. Change is part of nature, and this change continues today and will continue into the future.
To understand how the continents shape our world, we must first travel back in time to the very birth of the Earth. 4.5 billion years ago, the Earth is created from the debris left over from the formation of the Sun. Dust and debris collide and clump together. Once these clumps grow into objects about half a mile in diameter, they create enough gravity to attract more material. Slowly, these clumps grow into as many as 20 planets. As these new planets orbit the Sun, they begin to collide. One collision with the planet Theia, which creates the Moon, obliterates the surface of the Earth. The energy from the collision makes the Earth incredibly hot. At around 11,000 degrees Fahrenheit, it's more than 7 times hotter than the inside of a cremation furnace. Earth is a massive molten ball of boiling lava. This is primeval hell, where thousands of asteroids and comets bombard our world. But deep within the planet, a process starts that will lead to the first land. The heaviest elements, lead and nickel, sink down toward the center of the Earth to form a molten core. The lighter elements, including oxygen and silicon, rise toward the surface, where they erupt in volcanoes of molten rock. Slowly, the Earth's surface cools. Molten lava solidifies to form patches of crust, the seeds of the first continents. But even as the first land is born, it faces a battle to survive.
We were being bombarded by a large number of asteroids very early in the history of the planet. So there's a lot of dynamic change from being walloped by giant impacts, disturbing things.
Geology professor Sam Bowring is an expert in early Earth and the genesis of the continents.
When we had an early crust is an interesting question. I suspect we had an early crust from day one. The question is, how long was that preserved? When the Earth was being bombarded constantly by asteroids, the chance of preserving any small chunk of that crust was very low.
The relentless bombardment destroys the new planet's crust almost as soon as it forms. This recycling of the surface continues for many millions of years.
But as the flux of asteroids began to wane, and as the Earth matured a little bit, I suspect the early crust lasted a little bit longer.
Eventually, the barrage from asteroid impact slows down. The surface of the Earth continues to cool. But the Earth is missing one vital ingredient: oceans.
Where Earth got its water has been a controversial topic over the years. I think most people now think that many meteoritic bodies actually contain quite a lot of water.
Water carried by meteors and asteroids may form the oceans that surround the first continents. The Earth, 4.4 billion years ago. Our planet is now 150 million years old, and the first primitive landmasses have formed. They are not like the 7 instantly recognizable continents of today. They are just small rafts of rock floating on the mantle. But now a type of rock appears on the Earth's surface that will form the nucleus of future continents. A rock buoyant enough not to sink into the bowels of the Earth: granite. In South Africa, in the Causeway region southwest of Johannesburg, geologists examine ancient granite that has survived the ravages of time. These are the ancient remains of what some people consider to be the first true continent.
We're looking at the relics, the remnants of the first continental nuclei. This is one of the oldest, but certainly the best preserved continental nucleus in the world.
Geologist Alex Kisters studies how granite formed the first continents.
The rocks here are so important because they are remarkably well preserved, much better than anywhere on Earth. And that allows us actually to study processes that were involved in the formation of these early crustal rocks.
Kisters is collecting samples to date the age of the granite.
We're drilling these little rock cores, taking them out, and then sending off later onto the lab to be dated.
Dating rocks is a complex process because over long periods of time, the minerals can break down and reform into new rocks. Scientists look for an ingredient of rock that is tough enough to withstand the test of time. The answer is zircon, a crystal that is made inside molten rock as it solidifies. Even if the rock is destroyed, the zircons are durable enough to survive.
Zircon is an incredibly interesting mineral, and it incorporates uranium and excludes lead, and that sets us up to have basically nature's time capsule.
To illustrate this process, imagine that this hourglass is a newly formed zircon crystal. Sand in the top represents uranium. The sand in the bottom represents lead. Over millions of years, the uranium in the zircon turns into lead. Measuring the relative proportions of sand in the top and bottom of the glass reveals how much time has passed. Uranium's relentless decay into lead gives us a natural clock. Using this technique, geologists date this granite at 3.5 billion years old. This makes it some of the oldest rock on the planet. These rocks make up a major part of what is known as the Causeway craton. A craton is an ancient raft of rock, light enough to float on the mantle, and around which a continent will grow. Ancient cratons have also been found in the heart of the Australian and North American continents. The craton here in Causeway in South Africa stretches for 463,000 square miles. It's almost twice the size of Texas. Without granite, the craton and modern continental crust wouldn't exist. Granite forms when minerals in the crust melt, then react with water, cool, and crystallize. Because it is made of lighter minerals, granite is less dense than other rock in the mantle, so it floats on the surface and mixes with other rocks to form rafts of land. The Causeway craton is not totally built from granite. The oldest rocks here are these amazing pillow lavas exposed along the Causeway River. 3.5 billion years ago, they form under the sea as lava emerges from an underwater volcanic vent. Upon contact with water, the lava immediately gains a solid crust, which then cracks and oozes additional large blobs called pillows.
These rocks are amongst the oldest that we know. It's basically identical to pillow lavas that we see on a recent ocean floor or in settings like Hawaii.
The Causeway pillow lavas begin their life on the ocean floor, but are pushed up out of the sea to form part of a continent. But where did the granite come from? To create it, you need the right mix of minerals. A new theory suggests that life itself may have provided the missing ingredients. It may sound like an outlandish idea, but there's some evidence that living organisms that use photosynthesis appeared around the same time that the continents began to grow, 3.8 billion years ago. Scientists suggest that early organisms, microbes, help speed up the breakdown of rock emerging at the Earth's crust. Over hundreds of thousands of years, this rock breaks down into new minerals, which sink back into the mantle. Deep below the surface, they heat up and form granitic magma. The magma rises into the protocontinent, freezes, and forms huge solid rafts of granite. Now stabilized, the craton begins to grow, forming new baby continents. But cratons are not the only factors at work. More powerful forces are building up deep within the planet. Forces that have the power to rip apart landmasses and smash them together, changing the face of the planet forever. Four and a half billion years ago, the Earth forms. For many years, it is bombarded by asteroids and meteors. Slowly, the molten planet cools, and small landmasses form around cratons of granite rock. Massive forces from deep within the planet rip apart and smash these small proto-continents together as they grow into the large landmasses we see today. The surface of the Earth, the crust, is made up of a giant jigsaw of interlocking pieces called tectonic plates. The separate plates themselves sit on the mantle, the layer between the crust and the Earth's core. Although the mantle is made of rock, the heat and pressure deep down mean it's flexible enough to allow the plates above to move up to several inches a year. Evidence for the theory of continental drift was first proposed in 1912 by German scientist Alfred Wegener. He noticed that identical fossils were discovered oceans away from each other. Paleontologist Professor Mark McMenamin of Mount Holyoke College in Massachusetts is an expert in fossil records.
Wegener noted that a freshwater organism cannot cross a salty sea. And so if you find the fossils of a freshwater organism or a land creature on two continents that are now greatly separated by distance, they must once have been closer together.
By identifying like fossils on different continents, scientists can map which continents were joined in the past.
The fossil distributions will tell us where fossils occur and how the continents must have been juxtaposed. Fossils that are identical but occurring in very different parts of the world imply that the continents have drifted.
When he first proposed his theory of continental drift, Wegener was laughed at. The idea that continents could actually move was considered preposterous. The problem was, he didn't know how the continents moved. The missing mechanism wasn't discovered until the 1960s. Plate tectonics is powered by heat.
Plate tectonics is being largely driven by the fact that the interior of the Earth is much hotter than the surface.
The temperature at the center of the core is 10,000 degrees Fahrenheit. It's as hot as the outer parts of the sun. Much of the heat is left over from the collisions and massive bombardment during the early days of the Earth. The rest comes from radioactive decay of heavy elements in the core. Heat escaping from the core creates convection currents in the next layer of the Earth, the mantle. The process is like a lava lamp, where heat from the bulb at the bottom creates convection currents in the oil, pushing the synthetic lava upward. The heat melts part of the mantle and sends plumes of magma, molten rock, rising to the surface. It rises between cracks in the plates, creating new rock that pushes the plates apart.
I think that plate tectonics is virtually inescapable on this planet. It's an exceedingly efficient way to cool the interior of the Earth.
This formation of new rock splits apart and separates the plates and the continents sitting on them. Today, the majority of this new rock forms under the sea, creating vast interconnected volcanic mountain ranges that extend through all the major oceans of the world. One range can clearly be seen at the bottom of the Atlantic Ocean, along the mid-Atlantic Ridge. It stretches more than 12,000 miles from the sub-Antarctic to the Arctic. It comes to the surface in a few places. Iceland was created from volcanic lava, bubbling up at the junction between the North American and Eurasian plates. It's one of the few places on Earth that one can actually see continents being pushed apart.
We are watching here geological structures that you cannot really watch anywhere else. It's like a big textbook of geology. This is where the Earth's crust is being made.
Paul Einarsson, professor of geophysics at the University of Iceland, monitors the mid-ocean ridge where the continental plates are splitting apart. The ridge in Iceland is almost 3 miles wide. On one side is the North American plate, on the other side, the Eurasian plate. The rift here grows as new rock forms at its center, pushing North America and Europe away from each other. The Atlantic Ocean widens, and the two continents drift apart. Eventually, the Atlantic could become as big as the Pacific. To measure how fast they're splitting, Einarsson takes global positioning system readings at specific points along the plate margin.
We put the antenna right on top of the point, and then we can calculate the exact position of this point in the world with respect to the center of the Earth.
Although the ridge appears calm and there's no magma rising to the surface, Einarsson's measurements show that the two continents are drifting apart by around an inch a year. So by the end of the century, Europe and America will be almost 8 feet further apart. The movement in Iceland is typical of the processes shaping the continents since their birth 4.4 billion years ago. It's part of the great cycle of the Earth's continents. The new crust, created at the mid-ocean ridge, moves away, cools, and eventually sinks back into the Earth. When the first proto-continents formed, there were several interconnecting tectonic plates, constantly bumping and grinding against each other, pushing the new land over the planet. Today, the Earth has over a dozen plates, some colliding together, some moving apart. They are powerful enough to move a continent the size of North America over 3,000 miles in 200 million years. That's 15 miles every million years. The Earth, 3.4 billion years ago, and plate tectonics pushes the proto-continents together. They combine to form ever larger tracts of land. Scientists suggest that cratons combine with other cratons to form a supercontinent, a huge continuous stretch of land. It's called Valbara. Scientists are unsure of its exact shape or size, as only a few pieces, like the craton in South Africa, still remain. But Valbara's days are numbered. A rising plume of heat is growing beneath it. It's about to rip the world's first supercontinent into pieces. $2.7 billion years ago, Valbara, the world's first supercontinent, still dominates the planet. But plate tectonics, powered by heat from the Earth's core, is about to split it apart. Rock is a good insulator. When a continent gets very large, the rock traps heat beneath it. As it gets hotter and hotter, a plume of superheated magma builds up beneath the giant continental mass. The temperature continues to rise, and pressure in the mantle increases. Eventually, the crust can no longer contain the pressure, and the hot lava breaks through, ripping the land apart. You can see this process happening today in Africa. Heat from the Earth's core is ripping the continent apart. A giant rift valley runs from the Red Sea down to Mozambique. Giant cracks are opening up in the land. Volcanoes, like Kilimanjaro, mark spots where molten rock have risen to the surface in the past. In 10 million years, the eastern half of the continent will have split away. The molten lava trapped beneath the giant supercontinent of Valbara eventually smashes through the surface rock. The continent ruptures into several smaller pieces. These bits of land sail across the Earth. But nobody knows what happens to them or what the planet looks like at this time. The Earth is entering the Dark Ages. It is over 2.5 billion years since it was formed. It will be over 1 billion years before another supercontinent forms. The Earth is entering a deadly cycle of destruction and rebirth.
The theory of continental drift suggests that we go through cyclic phases of continental dispersion and then continental collision. And the continents then seem to move apart from one another and then collide with one another over maybe 100 million year or more time scale.
When a large continent splits apart, the separate pieces travel away from each other, pushed by the creation of new land at the ridge between plates. Because the Earth has a constant surface area, the same amount of land created must be absorbed into the Earth. This process happens at subduction zones at the junctions of plates. At a subduction zone, crust dives down into the mantle to be melted to form new rock. When the plate subducts into the Earth, it brings two pieces of land together. When they collide, a new supercontinent starts to form. It is now 1.1 billion years ago on our timeline, and the next known supercontinent has formed. Its name is Rodinia, and it holds almost all of the continental rock on the surface of the Earth. Still, no one knows exactly what it looked like, but at its heart is an area that will eventually become North America. 350 million years later, the cycle of annihilation and creation starts again as the buildup of heat beneath the surface of the Earth tears Rodinia apart. When Rodinia splits, it forms several smaller continents that for millions of years drift apart and then drift back together again to form Gondwana, a supercontinent in the southern hemisphere. Eventually, after several 100 million years, Gondwana slowly splits apart. Plate tectonics pushed the land back together to create the world's last supercontinent. It's a huge landmass known as Pangaea. All the continents we know today are here, joined together. Geologists are able to plot the continents' relative positions because 350 million years ago, there are numerous species on Earth, each living in distinct regions.
This specimen that I have right here is the first trilobite that was ever described from what is now the United States. It is exactly the same type of trilobite that occurs on the other side of the Atlantic Ocean in North Africa. So we know then that the trilobites in the old and new worlds must have been close together because they're so closely related.
The fossil records show that North America and Europe rest next to one another. The land where New York now sits is next to Morocco in North Africa. The Atlantic Ocean does not exist. The east coast of South America nestles against the western coast of Africa, while Australia, India, and Antarctica are joined to the southeast of Africa.
If we want to look at a picture of the world 250 million years ago, we're going to look at a world in which a four-footed creature could walk from one end of this landmass to the other.
Pangaea is one giant continuous landmass. It not only makes the world look very different, it also has a dramatic effect on climate. Because much of the land is located far from the sea, the climate of the interior changes radically from season to season. It gets very hot in the summertime and extremely cold in the winter.
You don't have the moderating influence of the ocean that we have today. So it's a very different world. And it's a world that in some ways is harsher and less hospitable, at least to life on land.
It's thought that the climate change caused by Pangaea's formation may have played a role in one of the largest mass extinctions on Earth. This event, known as the Permo-Triassic mass extinction, wipes out about 90% of all life on Earth.
It's been called the mother of all mass extinctions. I would consider that the formation of Pangaea, with its climate worsening effects, to be a contributing factor, however, and not the sole cause of the mass extinction.
250 million years ago, and the supercontinent of Pangaea is breaking up. The continents we know and recognize today begin to take shape. Over the next tens of millions of years, South America drifts away from Africa, North America away from Europe. Australia splits off from Antarctica, and heads north to warmer climes. The positions of our continents are becoming familiar, although their distinguishable features are not. The world's vast mountain ranges, the Alps and Himalayas, and its great valleys, like the Grand Canyon, are yet to form. They will emerge out of one of the biggest battles in nature, the battle between colliding continents. Earth, 100 million years ago. The continental map of the modern world is gradually becoming recognizable. But a battle is still raging between the continents that will change the face of our world forever and create some of the most extraordinary geological features on the planet. As the continents move slowly across the Earth, crust and rock is dragged back down into the Earth at subduction zones between the tectonic plates. But when continents collide at the plate junctions, sometimes there is a battle for supremacy. If neither plate will submit and drop down to be consumed by the mantle, then both the continents slowly smash and grind into each other. These pinch points of continental collision build mountains. The Alps are the largest mountain range in Europe. Higher than the Rockies, the Alps stretch from France in the west through Italy, Switzerland, and Austria to Slovenia in the east. Their formation is a direct result of a continental collision between Africa and Europe. The story of the Alps begins when the African plate breaks away from the South American plate. It starts moving toward Europe.
Without the plate movement, there wouldn't be any mountain on this planet.
Professor Gerard Stamfli of Lausanne University in Switzerland studies the processes that built the Alps. The African and Eurasian plates start to move toward each other, trapping a third, smaller Iberian plate between them. The three plates collide. The Eurasian plate is pushed downward into the mantle, chopping off the Iberian plate. The Tethys Sea begins to close. As the Eurasian plate grinds underneath the African plate, it pushes the Tethys Sea floor and part of the Iberian plate 600 miles north and many thousands of feet into the air. Rocks that started life on the bottom of the ocean end up at the top of the Alps.
Quite fascinating to imagine that if you are on top of the Matterhorn, you're actually staying on top of Africa. For geologists, Africa stops in the Alps.
Over the next 100 million years, the continents continue to smash together. New mountain ranges start forming around the globe. The largest, the Himalayas, form as the Indian plate charges northward toward the Eurasian plate. It moves at 2 inches per year, lining up a head-on collision. The movement of the Indian plate leads to a clash between two giant continents and creates some of the highest structures ever to exist on Earth. The incredible power of continental drift not only builds mountains, it also sculpts one of the world's most recognizable landmarks, the Grand Canyon in Arizona.
The Grand Canyon is a great scar on the surface of the Earth.
Geologist Ron Blakey has been studying the canyon for over 30 years.
It's just a wonderful place to come face to face with planet Earth.
The Grand Canyon is 277 miles long and up to 18 miles wide. At its deepest, it stretches down for over a mile. The gorge exposes the interior of the North American continent. It's like looking through the pages of a book. Each layer tells a story about the past.
One of the really neat things about Grand Canyon is as we go up the walls of the Grand Canyon, it's just like going through a time machine.
Layer upon layer of rock reveal the geological history of North America, from present day to 2 billion years ago. The deeper you go, the older the rocks. By studying the layers, Blakey can piece together the history of the canyon. He finds some of the most interesting evidence at the very top: fossils of ocean creatures.
Wow, this bed's the jackpot here. What we have is an extraordinary example of a Permian seafloor. The most important thing it tells us with respect to the Grand Canyon is that this area had to be near sea level when these rocks formed. Now it's 7,000 feet above sea level on the rim of the Grand Canyon. So something had to happen. Either the sea had to fall 7,000 feet, and we're pretty sure that didn't happen, or this landscape had to be uplifted 7,000 feet. We're pretty sure that happened.
250 million years ago, the canyon starts to form as a result of a collision between the Pacific and North American plates. They collide with such force, the North American plate thrusts more than 2 miles upward. What was once seabed rises over a period of 15 million years to form a vast plateau far above sea level. It stays that way for millions of years until it is transformed by water erosion. Six million years ago, several hundred miles south of the canyon, plate movements open up the Gulf of California to the sea. For the first time, small streams in the Rocky Mountains could empty into the ocean.
So if we're starting a stream at 14,000 feet in the Rocky Mountains and carving down to sea level, and the Grand Canyon just happens to be in the way, the Grand Canyon's going to get cut out.
These streams merge to form what is now called the Colorado River. It cuts down through the land, heading toward the Gulf of California.
It took a river to carve the canyon. The water has carved down through the rocks, layer by layer by layer, removing material out of the canyon and leaving the great void that sits behind me.
The Grand Canyon is a testament to the awesome power of the continents in shaping our world. Back on our journey, tracing the birth and death of the continents, it is now 20 million years ago. 2,500 miles south of the Grand Canyon, another plate collision is about to take place. The map of the modern world is almost complete. At this time, water flowing freely between the Pacific and Atlantic Oceans still separates North and South America. Over many millions of years, the Pacific plate begins sliding under the Caribbean plate. The pressure causes underwater volcanoes to erupt. Some explode with such ferocity that they create a range of small islands between North and South America. Over the next 17 million years, ocean currents deposit sediment in gaps between these new islands. Gradually, the sediment builds up and compresses to form land bridges between the islands. 3 million years ago, the Isthmus of Panama, a narrow strip of land, finally joins North and South America. It separates the Pacific and Atlantic Oceans. The flow of water between the two stops, and ocean currents must take new routes. This causes yet another change in the climate of our planet. It changes the movement of warm seas around the globe, disrupting weather patterns, possibly pushing the planet into an ice age. Many species are wiped out. The continents as we know them today are formed, creating the nice, hospitable environment for human civilization to evolve and thrive on planet Earth. But how long will it last? The forces that power plate tectonics are still active and will tear our continents apart once again. They will build a new world, one that may trigger another mass extinction and push humanity to the brink of annihilation. A view from space reveals Earth's continents as we know them today. There are 7 in total, but some are separated by a political divide rather than a geographical one. Africa-Eurasia is a supercontinent comprising of Africa, Europe, and Asia. It stretches from the Siberian Plateau in Russia to the Cape of Good Hope in South Africa. A spectacular route across 3 continents, incorporating dramatic climate change, vivid scenery, and diverse cultures. However, Africa-Eurasia isn't the only supercontinent on the planet. Because the Panama Isthmus links North and South America together, they too can be thought of as one vast landmass. And if the Bering Strait between Russia and Alaska were to freeze over, it would be possible to walk from Cape Horn in South America to the Cape of Good Hope in South Africa. A journey of around 25,000 miles. But this won't always be possible, for powerful forces deep below the surface continue to send the continents hurtling across the globe. A process that started at their birth 4.4 billion years ago, and one which will continue long into their future.
What we're observing at the moment is only a snapshot of the Earth's global cycle that has been undergoing for the last 4.5 billion years probably, and will be undergoing, even if we're not around anymore.
The global continental cycle has another impact on our world. It causes many natural disasters. Plate movement creates stress points, which lead to volcanic eruptions. As continents split apart, instability at the plate junctions causes earthquakes that rip apart whole communities. This one, on October 8, 2005, in Pakistan-ruled Kashmir, killed nearly 75,000 people and left up to 3 million homeless. And when plates subduct into the earth, their death throes produce devastating waves. The 2004 Indonesian tsunami is just one demonstration of the terrifying power unleashed when plates move. Such natural disasters are part of the continental cycle, and they're not going to stop.
Plates moving is something we have to live with. There's nothing we can do about it. It's going to happen. There are going to be big earthquakes in California. There's going to be a lot of damage. There's going to be loss of life.
In recent years, it seems as though natural disasters, powered by the movement of the continents, have been on the rise. But what we are witnessing is an increase in awareness, rather than an increase in the number or severity of natural disasters.
I think what we're really seeing here is a very raised consciousness of the public. With instant communication abilities, much more publicity is given to volcanic eruptions and earthquakes.
We are observers to only a very short period of the life of the Earth. If we could monitor earthquakes and volcanic activity caused by plate movements over millions of years, we would see a very different picture.
When you look at something over 10 years, you might have 10 major earthquakes. The next 10 years, you might not have any, but that's not significant. It just is related to the short period of time that you're making the observation at. When you start looking at hundreds, thousands, and millions of years, all that averages out.
It's impossible to predict exactly when the next disaster will occur. But it is possible to predict where it will happen. The plate boundaries. Map the location of earthquakes and volcanoes, and they line up with the cracks between plates. Plot where these plates will move over the next tens of millions of years, and the future looks bleak for many of the world's cities. So what will our world look like in the future? 50 million years from now, the Atlantic Ocean will widen, pushing New York further away from North Africa. Meanwhile, in the southern hemisphere, Australia will be on a collision course with Southeast Asia, and in Europe, Africa will head north, closing the Mediterranean Sea. A new mountain range will form where Italy and Greece once stood. Known as the Mediterranean Mountains, they will be as big as the Himalayas, extending from Spain across southern Europe, through the Middle East, and into Asia. 100 million years in the future, and the power of continental movements will render the surface of the Earth unrecognizable. The Atlantic Ocean will continue to widen, but a subduction zone will form along its western shoreline. The first sign of it can be seen today in the Caribbean, the Puerto Rico Trench. This trench will grow north and south along the east coast of North and South America. This vast subduction zone will consume the Atlantic Ocean, dragging Europe and Africa back toward the Americas. 250 million years in the future, intergalactic explorers returning to their home planet will find a world very different to the one in their records. There will no longer be 7 continents, but one gigantic landmass containing most of the land on Earth. They could find it a barren, frozen world. The explorers search for the remains of our cities, but when Europe and America collide, any cities along the coastlines will be gradually destroyed.
The geological future of New York is going to be rather traumatic. In the long term, New York is going to be at the site of a continental collision. North America and Europe are going to collide with one another and produce a distinctive suite of rocks which will eventually be crumpled between the two continents as they collide.
New York and its neighbors will be crushed and buried beneath the surface, leaving no more than a few remains.
In the future, geologists will be able to find remains of New York City trapped in the rocks themselves, either buildings or plastic bottles or old autos and their parts. All of these things will be incorporated into the fossil record and will be recognizable to a future geologist who knows what she or he is looking for.
Because of its similarities to past supercontinents, this future landmass is called Pangaea Ultima, the final Pangaea. Nearly all the landmasses in the world will be joined together. Pangaea Ultima will probably experience climate extremes, freezing winters and scorching summers. This deadly weather could have devastating effects on all life on Earth.
The implications for the human race are interesting to speculate about. Certainly, the disposition of the continents over time will affect Earth's climate, and that will in turn have an influence on which organisms survive, which go extinct, and could be a factor in future mass extinctions.
The world we know is inching slowly toward its own destruction.
The processes that shape the surface of the Earth are never going to change. We're going to have earthquakes, we're going to have volcanoes, we're going to have tsunamis and hurricanes, regardless of whether humans inhabit the planet. And so the planet will always be here, probably. Plate tectonics will operate for the foreseeable few 100 million years. The question is whether humans will be here to witness it or not.
But even Pangaea Ultima might not be the end of the story. The forces that created it may eventually rip it apart and start the cycle of death and rebirth again. But by then, the impact of colliding continents could have been too much for our species. With our cities destroyed and the climate severe, we may have already left our planet in search of a safer home.